It indeed is an honor to be associated with the name Wallace Stegner, one of my literary giants, but also to be asked to lead off this symposium. I'm going to try to frame the next 2 days for you and show you images and ideas that will be discussed in much greater detail by individual people. So I'm only going to touch on a variety of things, but I've organized my thoughts in the following way. With respect to global climate change, and in particular into global warming, I'm going to follow the 4 questions. What do we know? And then as a scientist, we must ask, what do we not know? And then what can we do? And finally, the sermon, what should we do? And so we'll proceed in that way. And we'll come back and answer the question 30 minutes from now, is it just hot air? The first slide, starting out in the sequence of what do we know, is that we know that the Earth is warming in the last century. So this is the graph that is in some ways, the fundamental graph of evidence for global warming. It's the meteorological record. The vertical axis here is temperature, either in Celsius or Fahrenheit, over the last 150 years. Now it goes back only to 1860 because that's the period of time when we first get a sort of globally comprehensive set of weather stations that can report from which we can calculate a global average. So the take-home message here is that the Earth is warmed by close to a degree C, but it hasn't warmed uniformly. It's really important. So we say scientifically that it isn't a monotonic increase. It pops up and down a little bit. Rather important, goes up quickly in the early part of the century, stable or decreases slightly from 1940 to 1970. Point made, lots of which was made by Michael Creighton in a misreading of the natural variations of the Earth. And then the last 2 or 3 decades now, 1998 was a very warm year, and it was just reported recently that 2005 was the warmest year in history for the Northern Hemisphere. So factoids, a degree of warming, not even in time, nor is it even in space. This is the same distribution as we saw in the last slide. This is the change. It's rather a historic slide now, but it's one that woke many of us up. This is the change from 1860 to 1985, 1880 to 1985. So it's a 100-year change. And the axis is the change in temperature in degrees C. So oranges and yellows and reds are warming. Blues and greens are cooling, and the fact that it's an orange to red map and not a blue-green map says the same thing as the last slide. But now it says also that just like the Earth doesn't warm uniformly in time, it doesn't warm uniformly in space. And the most important thing is that there are a few areas that in fact have cooled during this period of time, but the most important thing are the dark red colors at high latitudes. So we have 2 speakers, Mark Serres and Sheila is going to speak today about the Arctic. And so we'll focus on that. We call it the latitudinal amplification of the global warming signal. So global warming of about a degree, not even in time, not even in space. Uneven in space. A second measure of global warming is the glaciers. And we have 2 people speaking over the next 2 days on the disappearance of glaciers. This is one of them. This is the Rhone Glacier taken in the year 1850, the retreat of the glacier in 1928, and then in 1980-81. You could measure warming if you ran around the world and measured the ice volume in every glacier on the world. It'd be a wonderful project for graduate students, right? We don't have that, but fortunately when the ice cubes of the world melt, they all melt into the same bathtub. And so we can get a measure of the melting just by measuring the level of the bathtub, and the Earth's bathtub, of course, is the oceans. So a measure of warming or climate change is the change over the same time span, here's the last 200 years, of the world's oceans. This is a very noisy noisy graph, and we really only know it really well since satellite coverage in the last 20 years or so. But whichever way you cut it, you get the same message that the world's oceans have gone up about 160 millimeters, 16 centimeters. I call it 160 millimeters in about 160 years to make the math easy. So that means the oceans are going up at about a millimeter a year. Probably a third of that change is caused by melting ice right now, and two-thirds of it is caused by thermal expansion of the water column as the Earth warms, but that could change very rapidly. That could change very rapidly as we start melting the ice caps. A third independent measure of whether the Earth is warming or not comes from my own work, and I'll take a little bit longer to explain this. It comes from information not above the ground, but below the ground. And the idea here is if you put a poker into the fire and then take the poker out of the fire, by measuring the temperature of the poker, you can say it has been in the fire, even though it's not in the fire now. And by measuring how far the heat wave has gone up the poker, you can say how long it had been in the fire or how long ago it had been in the fire. The Earth responds in exactly the same way. If you held a blowtorch on the surface of the Earth, or warmed the surface of the Earth, that warming would penetrate down into the subsurface. Rocks are a poor conductor of heat, so if you did that 100 years ago, that heat wave would have penetrated about 80 meters into the subsurface. If you did 1,000 years ago, it would have gone 300 meters into the subsurface. It scales with the square root of time. The good news is that the last millennium of Earth history, in terms of Earth's surface temperature, is recorded in the upper 300 meters of the Earth's surface. So a group of us, some included in this room, make it a habit of going out and measuring temperatures down in drill holes. So we measure borehole temperatures. This is our setup here at the university. So we have a reel of cable going over a reel. We lower a thermometer down into the subsurface, measure it with a measuring resistance bridge, and log it onto a laptop computer. And the thought experiment you could do with me, if you measure this temperature, subtract out the background of the Earth's temperature, then if the Earth's been warming, the temperatures near the surface will be over on the positive side. If it's been cooling, it goes negative. So this is totally independent from measuring sea level or the type of thermometers you have in weather stations. And it also is not restricted to the last 150 years beyond 1860. The advantages are there's a measure of temperature. Unlike tree rings, which are used to reconstruct temperatures, it's not seasonal. Thermal processes are a good integrator. It tracks air temperature. We know that in part because we put a weather station right on top of the borehole. And here's a very happy graduate student logging air temperatures. So for the last 10 years now, we've measured every 30 seconds. We've measured air temperatures and ground temperatures, so we know the tracking process. So the results of this work and many others shows like this. So here's depth down to 200 meters. This is an arbitrary temperature scale with half a degree of temperature there. So the temperature down at considerable depth is not disturbed, but as we come towards the surface, it moves over. It's warmed by about half a degree for southeastern Utah. For Nebraska, it's about a half a degree. For the Canadian Shield, it warms about a degree. And for Alaska, it's warmed by 3 or 4 degrees. So this is an independent method. And I would say that from this we can reconstruct, again, a temperature change versus time. So here's temperature change versus time. Here's the meteorological record, back to 1860. Now, many of us are trying to reconstruct that in past. All of these spaghetti lines represent what we call proxy methods of reconstructing temperature. The boreholes weigh in, depending on the type of analysis, either with this purple line or this solid line, giving us none of the detail because heat diffuses out in time, but giving us a baseline temperature from which we can take the modern warming. Many people will say, well, how do you test your ideas of any of these reconstructions? And the idea is that you can, because the solid dots here in temperature depth space, the solid dots are the northern hemisphere average. So for any of these curves, you can run it into the ground and say, what would a borehole look like if it had been recording in that time? And so you can distinguish between the top curve, which is the Mike Mann's hockey stick reconstruction, that absolutely misses the reconstruction here. So we know that it's warmed more than that reconstruction. So my point is that we have meteorological records, we have sea level change, and we have borehole records and the proxy records, and they all say that the Earth is warming. Now, there are many other methods that are not so quantitative that also say it's warming, and much of the discussion over the next 2 days will be from biologists and meteorologists and ecologists. So here's one published in Science. Biology is shifting. Mexican jays are having their young 10 days earlier than they did 3 decades ago. Many people will speak about the lack of sea ice in the Arctic, and we'll hear about polar bears multiple times. There are severe economic impacts. This is one, in the Arctic, you travel when the ground is frozen. So these are the number of travel days versus time 1970 to the present time. So it's gone down from 200 travel days in the year down to about 130 travel days in the year. This has huge economic impact. A slightly more whimsical but also interesting ecological and economic impact is the concern that the wine industry now has about global warming, and in part the water changes and water availability that might come about with climate change. I checked in Google yesterday, so I Googled wine and global warming and got 1.2 million hits. So this is and published in notable journals such as the Climate Change, Journal of Climate Change, and also in Wine Spectator and other places. My graduate students put the polar bear in the picture, and they said, well, you can call that the Coca-Cola polar bear, and the choice is no longer Coke versus Pepsi, but is now Chablis versus Sauvignon Blanc when it gets up to the north. And I said, well, it isn't very realistic. They say it's just as realistic as some books that have been published like by Michael Creighton recently. So moving on to some more things that we know. We know what makes the Earth's surface temperature. Planet Earth is a certain distance from the sun, so the temperature is almost completely controlled by our distance from the sun as a radiating body. If you put an atmosphere around the Earth, the atmosphere will do two things. Clouds will reflect sunlight back into space. About a third of the radiation comes in. That will cool the Earth, but the greenhouse gases in the atmosphere will warm the Earth. And the combination of both of those effects with the solar effects gives us a habitable planet in the biological sense that we know it. The average temperature of the Earth is about 15 degrees. That's perfect. It's above zero, which means we're not an ice planet. It's below 100 degrees Celsius, which means we're not a vapor planet. So 15 degrees C, which has existed, fluctuated in part over time, but that's the average temperature of the planet. The danger is, so that's the beneficial greenhouse effect. The danger is that growing population is upsetting that balance, and we'll move to that. Now, another thing we know is the details of the greenhouse effect. So this is a rather technical slide, but it's basically radiation out from the Earth. We call it Earth light, just like sunlight is coming in. So if you go out to a satellite and look back at the Earth, you can measure Earth light going out. And what we have is, if the Earth didn't have an atmosphere, then it would simply radiate along this smooth white line. But the actual radiation going out from the Earth is measured as this jagged line, which is deficient, so radiation is not getting out. And we know from theoretical and observational studies why it isn't getting out, so we can identify these gaps of radiation absorption with different gases, and those are what we call the greenhouse gases. So we have water vapor here, methane, ozone, but the really big one is carbon dioxide. And that's why we're concerned about CO2. It's not that there are not other greenhouse gases, but not only is it really important, but it's the anthropogenic part. So water vapor is also important, but that's in the natural background. So I'm going to focus for a few minutes now on CO2. This is, in the same time scale, what CO2 has been doing in the atmosphere for the last 300 years, 1700 to the present. Carbon dioxide concentration measured in parts per million. For a long time, it's at a background of roughly 260 or 270 parts per million. Industrial revolution, combustion of fossil fuels, and we're now up, it was reported at the American Geophysical Union meeting in December, we've now just passed 380 parts per million. So this is the human impact. Just a quick word about this. Each of these points is an annual average, but in fact, the measurements are made hourly, so you can make a more continuous curve. These are annual cycles. So this is the breathing biological Earth. As the leaves come out, principally in the boreal forests of the northern hemisphere, suck down carbon dioxide, and in the winter give it off again, and they increase. I mention that because the amplitude of this up and down is really important. It's about 6 parts per million. Remember that number, 6 parts per million. So here's the rise in carbon dioxide, but you might be saying, wait a minute, Chapman, you know better than Creighton, because we know how you measure parts per million in 1990 and 2000, but where were the mass spectrometers back in 1700 to measure atmospheric gases in parts per million? Well, you either have to have really old instruments that were really good, or you have to have old air. And here's where we get the old air. We get them out of glaciers and ice fields. So you simply, if you want atmospheric concentrations in the year 1700, you simply have to go to a glacier like this. This is a slide from Lonnie Thompson, who's going to be speaking at the symposium. Each of these lines is an annual ice accumulation. So you simply start at the top, 1998, 1997, 96, 95, count down to 1700, take that ice, which has got bubbles of air in it, break it into your instrument, and measure the concentration. And the reason that we know that works is that even though the instrumental record is made in Hawaii, and these ice cores are made elsewhere, there's a seamless transition from the ice core record into the atmospheric, into the instrumental record. So by that way, we can go and look for really old ice and measure what the Earth's atmosphere was doing back in time. So now we'll shift timescales hugely. Remember, we've been working with 150, 200 years. So this timescale is now 150,000 years. This is a really, really important slide because it says something about the natural variation of the Earth without humans involved. We always get the question, well, doesn't temperature go up and down in the Earth by itself? Don't atmospheric carbon dioxide go up and down? And the answer is yes. But that's not an excuse for saying, well, we wait long enough and it'll go down again by itself. The question is there anything really unusual about the current state of affairs? So I would ask the following questions. What is the limit? First of all, we said that carbon dioxide, which is the blue curve, and the temperature on the scale over here in carbon dioxide, does it go up and down by itself? The answer is yes. What are the limits? The lower limit is about 200 parts per million. Over the last 150,000 years, the upper limit has been about 300 parts per million. There's where it was in 1800. And what are we now? we're 380, so we're off the scale already. And I would say that this is different, quite different from anything over the last 150,000 years. So while this is a really interesting question of where have we been in the past, what's a more interesting question than that? Where are we going in the future? So I want to make an argument and recalculate this curve 100 years in the future and show the curve. The argument, I think, is quite simple. We know what causes CO2. It's the burning of fossil fuels. That's required by our energy appetite and by the number of people on the planet. So let's look at those three things: people on the planet, our energy appetite, and how we make energy. So the first one is a slide that I think most people would have in your heads. It's the growth of human population over this same 300-year period, doubling time of 150 years, doubling time here of 44 years. Just before the year 2000, we passed over 6 billion. And I'm fond of saying that Y2K is a non-event, right? Computers were supposed to crash, planes fall out of the sky. Nothing happened. The big event at that point in time in Earth history is Y6b. It's the year that the human population passed 6 billion. So it passed 6 billion on December 16th, 1999. Guess what it is now? I checked on Pop Clock. So you can Google, it's short for population clock, and it'll give you a little digital clock. It goes tick, 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 tick. We're adding people about 2 per second to the planet. So it was 6 billion in the year 2000. It's 6.5 billion this morning. 6,501,000,000 this morning. So population is going up and will go up. So increasing population, but this is a really interesting slide as well. This says, how do we live? It's the standard of living measured as a distributed index of these three things versus the per capita energy consumption. There are three kinds. Each of the points on the graph is a country. There are three kinds of countries plotted. The really big ones, India and China, are plotted as blue triangles. Those are the countries with population more than 1 billion. Next biggest countries are the ones that are red dots. Those are countries more than 100 million. And the other yellow diamonds are many other countries in the world. And the take-home lesson here is that the way we have constructed society and technology has it that if we increase the standard of living, we basically slide out to the right-hand side of this curve. And there we are as winners. So the USA out here, and I have to have full disclosure, I'm a dual citizen. So here's one of my countries, there's the other one of my countries. That's Canada. So the US and Canada are out there. So more people, but as standard of living increases, remember this is about half the world, more than half the world down here. If we increase the standard of living and technology, then we slide up to the right and consume more energy. So more people, each person using legitimately more energy. How do we produce our energy? So this is energy consumption in the world over the last 20 years. So not only has energy consumption grown, but it's roughly that our energy is produced about 90% by fossil fuels. So each time you produce a joule of energy, so much CO2 goes into the atmosphere, so we can go back and recalculate that curve that we showed you before. Here's the last 150,000 years. The blue curve is CO2. Here's where we were, here's where we are now, and there's where we're going. This is doubled CO2 up here. So we're running an experiment with the planet that we've not run before. So that's a sobering thought. Warren Washington, who's speaking, will talk quite a bit about what the prospect for that is. That's what we know. What do we not know? There's a really interesting book that's just been published by Henry Pollack, who's going to be speaking in this symposium. This is the cover of his book, Uncertain Science, Uncertain World. And Henry makes the point that we don't know everything. We live in an uncertain world, but that's the basis for scientists, but it drives policymakers and politicians crazy. Right? So if you're not certain about something, then how can you act? And we'll wait until we have more data, but that's just not a possible option. So I'll just advertise Henry's book and a very nice statement made by Sir John Houghton about it. What we also don't know is some tricky feedback mechanisms. For example, in a warmer world, you get more evaporation off the oceans. Water is a greenhouse gas that should warm the planet even more. That's a positive feedback. However, if the water droplets go into clouds, clouds can reflect sunlight back out and cool the planet. That's a negative feedback. So that's an intensely researched subject right now, and the answers aren't yet in. The person speaking right after me, Bill Curry, will talk about the oceans, and the key really is in the oceans. For two reasons. They're the big heat reservoir in the Earth, and they control climate in terms of ocean currents, but also because that's where the carbon is. So this is the inventory of carbon, 700 gigatons in the atmosphere, 35,000 gigatons in the oceans. So the dynamics of getting carbon dioxide into the water column or out of the water column is critical. Now, so what can we do? There's lots of things that we can do. Sheila Carter from the Natural Resources Defense Council is going to be talking, so I won't steal her thunder, but this is from their website. There's many things that an individual can do to cool it. This is from a cover of Maclean's magazine. It's the Canadian equivalent of Newsweek or Time. This is from last year, last January, 101 days, ways to save the environment and money. Tune your car, save $400 a year. The one I like is that if every household in America went home tonight and replaced a 100-watt light bulb, incandescent bulb, with a compact fluorescent bulb, you could take 500,000 cars off the roads in terms of carbon dioxide saving. This is because compact fluorescents use a quarter of the electricity of incandescent bulbs, but we've got another big jump to make into LEDs, light-emitting diodes. You notice when you go to a stoplight now and look up, there are these little pixelated stoplights. They're fired with red and green LEDs that use a seventh of the electricity. So there are big advances to be made. I just had to show you this. Jan Nystrom put in your program a comment about me commuting to the university for the last 30 years on my 10-speed Peugeot. So here it is. So this is my way of getting, I bought it from a graduate student secondhand for $75 30 years ago. So my capital costs on getting to and from work are now $2.50 a year. Double it for tires and a new seat and so forth. So we're up to $5 a year. This is a picture of my backyard. Don't say everybody has to live this way, but here's our bicycle. There's our eco lawnmower. There's our new invention. It's a solar clothes dryer. Utah is a wonderful place. You sun dry in the summer. You freeze dry in the winter, so forth. These are my tomatoes, peppers, eggplants, and so forth, and my grapes on the backyard. When the average produce in America travels 2,000 miles to get on your table, the average produce travels 2,000 miles to get on your table, you feel really good when you walk 50 feet to put your produce on your table. But here's the rub. I don't know how many of you have gone to the website called Ecological Footprint. So it asks you can Google Ecological Footprint, and it'll give you a questionnaire and says, how do you live? How big's your house? How do you get to work? What do you do, etc. And then it'll say, if everybody on the planet lived the way you lived, we would need half a planet, 1 planet, 10 planets, etc. So the Chapmans, living in a fairly conservative way, a mile from campus and so forth, living the way you see it, it takes us 4 planets to support our lifestyle. It's because we get on airplanes. It's because we travel. But it just shows that we're in an unsustainable fashion for that. Here's another one. It says, what can we do? We can reforest. Remember I said that reforesting the leaves coming out drops CO2 by 6 parts per million, so that's not the total answer. What can we do as a global society? It's imperative that we reduce population growth, that the Earth turns over at 8 or 9 or maximum 10 billion and then maybe reduces in time, but doesn't grow to 12 billion or so. There's lots of problems. In Utah, we only have to look in a mirror. The recent legislature failed to pass the pill bill for the 8th year in a row, but passed abortion legislation. So we have something to work on here. To the students in the audience and the engineers at the U, I say, if this were a board game, this is where you have to land. So we're not in the winning place out here. In a sense, we're out in right field. And what has to happen is these countries have to move up into here. And then in terms of energy production, we have to both reduce growth and conserve and switch sources. What we will certainly hear about in our lifetime, most of these solar, wind, geothermal will get us 10 to 15%. Very important because they extend the time and give us a lead time, but I think it's almost certain that we're going to go into a nuclear world. Somebody told me recently that China is planning 30 nuclear power plants right now. There are 50 nuclear power plants globally planned. Companies are getting it. This is a full-page ad in Time magazine. Is there a choice? Ignoring alternative energy is no alternative. What used to be known as British Petroleum is no longer. BP is beyond petroleum. Full-page ads. They're an energy company now. Until very recently, we thought this is just because Royal Dutch Shell is centered in the Netherlands, and BP is centered in Britain. But we now, thankfully, have domestic oil companies or energy companies. So this is Chevron. I salute their sponsorship for this symposium. So here's the text. They've got a website, willyoujoinus.com. I suggest you look at that as well. And then the last point, I hope that some discussion over the next 2 days has to do with the question, won't steps taken to reduce CO2 ruin our economy? Is the economy stupid, right? And Jim Mills, a colleague of mine, showed me this equation. He said, you can't relate carbon directly to the economy. The equation doesn't balance. But if you write it this way, it does. So C equals C over energy, energy over GNP times GNP. Cancel energy, cancel GNP. So the equation says C equals C, and my math teachers in high school would be quite relieved. Okay? But what are the terms? What are these terms? This is the carbon intensity. So how much carbon do you burn to produce a unit of energy? Okay? So coal and wood are terrible. Oil is better. Natural gas is better. But things like wind and solar and nuclear are extremely better. This is the reciprocal of efficiency. So what do you produce for a unit of energy? And many people at this meeting will talk about the efficiencies to be gained in our society. So there's no reason why we can't drive this term down, and as people would say, grow the economy while you're driving carbon in the atmosphere down. Our future certainly has to do with wind. I want to salute the students from the University of Utah who 2 years ago voted themselves a tuition increase of $1 a semester to go towards buying wind power for the University of Utah. That's $56,000 a year that goes towards buying wind power. So that's certainly part of our society. So that's a flavor of what we're going to get over the next 2 days. Many people are going to take an individual slide or an individual theme and expand it in great detail. But I want to leave you with maybe 6 take-home messages. Warming is real, Michael Creighton notwithstanding. The feedbacks are complex, and we probably don't know all of them. A couple of people are going to speak about whether losers outnumber winners. Sheila Watts-Cloutier, I think, is going to tell us that there are lots of losers in the Arctic. I didn't mention about greenhouse gas emissions and their residence times. Jim Erlinger will say that once you put carbon dioxide in the atmosphere and just leave it, it won't come back to the normal for about 200 years. That's why we cannot study things longer, but we have to act right now. And then many of us will make this point that the prudent path has benefits beyond reducing the warming on the planet. Thank you. I'm told we have 5 minutes for questions, so I'll take the questions. I can. Yes.
When you were talking about the finding carbon in the ice, and in the past, about 150,000 years ago, there was 300 parts per million volume of carbon in the atmosphere at that time, and now we're at approximately 380 parts per million. What were the causes of such a high amount of carbon in the atmosphere at that point?
Yeah, I want to repeat the question not only for the people in the back, but for the other room that may not hear. The question was, if you go back and look in the ice cores, carbon dioxide fluctuated between about 200 and 300 parts per million. The question is, why was it fluctuating, or why was it at that value?
Why was it fluctuating? Why was it at such a high number? And it also looked like a large peak.
Yeah, the peak, I didn't go into the details, but the variations through time have dominant periods of 20,000 years, a little more than 40,000 years, and 100,000 years. We call those the Milankovitch Cycles. So these are the variations in the Earth's orbiting parameters and the radiation received by the Earth that put us into natural ice ages and bring us out of ice ages. And with the changing temperature with radiation goes feedback mechanisms that will suck carbon dioxide into the oceans and then release them from the oceans. But there are also, I just want to illustrate one of the complex feedbacks, and maybe Bill Curry might speak about it just a little bit. If you get a colder and drier climate, for example, in Asia, then you get dust storms that blow dust over the Pacific. The dust has iron coatings on it. So you fertilize the ocean with iron, which is a fertilizer for phytoplankton. The phytoplankton grow, and their shells are made of calcium carbonate, right? So that sucks the carbon out of the water column, creates a disequilibrium, and pulls carbon out of the atmosphere. So these fluctuations go on all the time. But we shouldn't allow just knowledge of natural variations to say we don't have to do anything now, because the rate of change now is very much different from anything we've seen. I showed you 150,000 years, but in fact the record goes back, I think the oldest ice is now sort of 450,000 years in Antarctica and in Greenland. Another question.
Do you think our long-term goal should be no more than a doubling of CO2 concentration in the atmosphere, or should it be less than that? Or what time period do you think about that?
The question is, do I think our goal should be a doubled CO2, the time scale for changing it, or what do I think about that? I think that we need to take immediate steps to reduce emissions of carbon, partly because of the long time frame. David Sandlow is going to speak late this afternoon on policy issues. I'm going to sort of buck that off to him. Are you willing to talk about that? He says yes, so that's the last talk this afternoon. Other people have said, why worry because we're going to run out of petroleum, which we probably are in 50 to 100 years, we're producing a third less petroleum now than we did in 1969. The world is just going over the top in petroleum production. So won't that solve our problems? It doesn't unless our energy appetite goes down. So if we move from petroleum burning to coal burning, then we exacerbate the problem. So I think to build a lead time, we want to decrease carbon emissions as much as we can, and the earlier the better. So that exhausts the question time. Are you going to introduce the next speaker? Why don't the next speaker is Bill Curry from Woods Hole Oceanographic Institute, and he's going to tell you about the oceans.